Okay, we're going to move on to the last three types. The first one is nomenclature of inorganic acids. How you recognize an acid is when you look at the formula, you will see an H listed first because acids are things by definition that will give off hydrogen ions in solution. So if you look at the examples HCl, HNO3, H2SO4, those are all acids. There is one exception to the rule, and that is for acetic acid, and that is CH3COOH, where the acid H is the one on the right side. This is the way it's written in organic chemistry, but the way that we're going to write it is what you see here, HC2H3O2. So it's a hydrogen ion with an acetate ion. This is the inorganic style, which we are currently using. So to name acids, in order to explain the sequence, I'm going to use HCl, HClO, HClO2, HClO3, and HClO4. So the rules are for binary acids. Binary acids are when the X in HX of an acid ends in "ide," like chloride, sulfide, bromide. When you are naming them, those acids will begin with hydro. So HCl up above is hydrochloric acid. HCl is binary, and all binaries are named the same way. They start with the prefix of hydro. They use the root of the anion. For HCl would be chlor, and the suffix IC. The word acid is used as the second word in the name and must be there because that's what tells you it's an acid. So the name of HCl is hydrochloric acid. Other binary acids are HF, HBr, HI, and H2S. When an anion in the formula ends in ITE, therefore it's going to be one of the polyatomics. The acid name is using the stem, so H2SO3, I'm going to use that example. H2SO3, the stem is sulf, so SO3 is sulfite, so I use the first part of that sulf, and then I take off the ITE and I replace it with the suffix OUS and the word acid. So H2SO3 is sulfurous acid. HClO is an acid that has a polyatomic ion. You must recognize the polyatomic ion in the formula. There's no other way to figure out the name. If you don't recognize the polyatomic, then you're not going to be able to figure out what the name of the formula is. The polyatomic ion ClO- is hypochlorite. So anytime you see the "ite" suffix, you change it to OUS and add the word acid. So since ClO- is hypochlorite, it becomes hypochlorous acid. When the anion ends in ATE, the acid name is going to use the anion stem with the IC suffix followed by the word acid. So H3PO4, PO4 is phosphate, so that becomes phosphoric acid. HClO3 has a ClO3 minus polyatomic ion, and ClO3 minus is chlorate. So since it ends in ATE, I'm going to take the chlor part of it and put the word "ic" and then the word acid. So HClO3 is chloric acid, where HCl was hydrochloric acid. Two keys for naming acids. One, you have to recognize when a polyatomic ion is present, and two, you have to know its name. Only then can you change the ITE suffix to OUS and the ATE suffix to IC. So, we look at the polyatomic ion chart. Any of them that end in ATE will become an ic acid, so sulfate, H2SO4 is sulfate, so that becomes sulfuric acid. If it's an ITE, that becomes OUS acid, so HNO2, NO2 is nitrite, so that becomes nitrous acid. If it's an ide, that needs the hydro first, the stem, and the suffix IC. So H2S would, since S is sulfide, would be hydrosulfuric acid. I'm showing you the root and where the names came from, so you can see the one that I chose. And the last one is over here because it's monatomic. All right, I want you to pause right now and try to do both the names and the formulas. When you're doing the formulas, you're going to have to balance the charges with H being a +1 charge. Okay, welcome back. If you did it properly, H3PO4 should be phosphoric acid. H2SO4, sulfuric acid. HF, hydrofluoric acid. H2CO3, carbonic acid. HClO3, chloric acid. And HNO2, nitrous acid. On the right side, going from the name to the formula, you have to look up the anions. So hydrobromic acid comes from bromide, so that would be HBr. Nitric acid comes from nitrate, so that would be HNO3. Notice both of them are just the H and the anion because they're +1 -1. If you get something like phosphorus acid comes from the phosphite, which is PO33-. So since it's PO33-, I need 3 H's to balance that because H is plus. Hydrocyanic acid, it's hydrogen cyanide, but like I said, there's a twist in it because most of the hydro acids, like hydrofluoric or hydrobromic, are using just nonmetals. But with cyanide being an IDE, if it's an IDE suffix, I'm going to use the same rule. So I'm going to put hydro in front, and then the cyanide is going to become cyanic. So it's hydrocyanic acid. And cyanide's -1, so I need 1 H. Sulfuric acid comes from sulfite, so that's H2SO3. And permanganic acid comes from permanganate, so that's HMNO4. Now, we're going to now move on to something that is totally different, molecular compounds. A binary compound we know is made of 2 different elements. There can be one of each or more than one of each. So I have 2 examples. I have CO, NO, those are molecular compounds that have one of each element, and there are others that have different combinations. BF3, it has boron and fluorine, but it has 1 boron and 3 fluorides, just like OCl2. There's 1 O, 2 Cls. This lesson is going to show you how to name binary compounds from the formula when 2 nonmetals are involved. Now, there will be no metals in this. There are no cations, there are no charges, there are no crisscrossing, there are no parentheses. It is just 2 nonmetals. So what's going to happen here is one of the nonmetals is going to be acting in the positive role and the other in the negative role, even though they're really just sharing electrons. The thing is, as I said, you don't need to know charges since the formula comes right from the element names and their prefixes. Be aware of the heavy use of the Greek number prefixes used in the lesson. So mono means 1, di 2, tri 3, tetra 4, penta 5, hexa 6, hepta 7, octa 8, nona 9, and deca is 10. So we're going to start with the N2O formula. What you're going to do is the first part of the name is just the name of the element. But because N2 has a subscript of 2, I have to indicate that subscript of 2 as a prefix. So it's going to be dinitrogen, and then the second one will always get a prefix. Since there's 1 O, it will be monooxide, but we never put 2 O's together, so it will be dinitrogen monoxide. Same thing, number 2, I have 1 nitrogen and 2 oxygens, so that one is nitrogen, and the 2 prefix for the oxide is dioxide, just like carbon dioxide is CO2. IF7, the first element's iodine, so I call it iodine. You do not use prefixes on the first element if there's no subscript, so you call it iodine, not monoiodine. The second step is I'm going to use the ide form of fluorine, which is fluoride, and since there are 7, I'm going to use the prefix hepta. So IF7 is iodine heptafluoride. N2O5. I have 2 nitrogens, so that's dinitrogen. I have 5 oxygens, so that's pentaoxide. But we do not use the A in penta for pentoxide. The last one here is XeF2. Xe is xenon, 2 F's is difluoride. Notice I did not talk about charges, crisscrossing, or anything. So N2O4, 2 N's is dinitrogen, 4 O's is tetroxide. So I want you to do these first 15. So pause and try them. All of them are going to use the molecular naming rules, so they all need prefixes for at least the second element. Okay. Number 1, tetraarsenic decoxide. 2, bromine trioxide. 3, boron mononitride. 4, dinitrogen trioxide. 5, nitrogen triiodide. 6, sulfur hexafluoride. 7, xenon tetrafluoride. 8, phosphorus trichloride. 9, carbon monoxide. 10, phosphorus pentachloride. 11, diphosphorus pentoxide. 12, disulfur dichloride. 13, iodine dichloride. 14, sulfur dioxide. And 15, tetraphosphorus decoxide. Notice for all of them, the only time I use a prefix on the first element is if it has a subscript. Otherwise, I just name the element. And the second one, notice, will always use the IDE form. The reason they did that is so if you see the name, you can know the order of the elements. But notice all of our binary molecular compounds will use prefixes on the second element and prefixes on the first if it has a subscript. Try these 15. Uranium hexafluoride, oxygen difluoride, chlorine dioxide, silicon dioxide, boron trifluoride, dinitrogen pentasulfide, carbon dioxide, sulfur trioxide, xenon hexafluoride, krypton difluoride, bromine pentachloride, sulfur tetrachloride, phosphorus trichloride, xenon trioxide, and osmium tetroxide. All of those are that way using the molecular formula to name rules. Now, given the name to the formula, it's basically the same thing except in the opposite direction. And most people find these very easy because looking at the name, it almost gives you the formula. So instead of walking through all this, example 1 is dinitrogen trioxide. So that means 2 N's and 3 O's. If you look on the bottom, N2O3 is dinitrogen trioxide. Carbon monoxide, 1 carbon, 1 oxygen, CO. Notice in monoxide, it is mon, not monooxide, just as before. Whenever you have oxide, if you have a double vowel, you chop off the one that's in the prefix, in the suffix. So we have BrF5, so that's bromine, and there's 5 F's, that's pentafluoride. P2O5, that's diphosphorus, 2 phosphorus, and 5 oxygens, O5. Iodine heptafluoride, iodine is I, heptafluoride is F7. Try these 15. Notice number 3, it should be boron monophosphide, but it's listed as boron phosphide. That's actually incorrect. So, if you've done these should be your answers. ClO, OF2, BP, N2O, NF3, SCl4, XeO3, CO2, P2O5, PCl3, SO2, BrF5, S2Cl2, BF3, and ASO10. Please do the other 15 before moving on. 16. SiCl4, KrF2, ClO, SiO2, BCl3, N2S5, CO, SO3, N2O3, N2O, XeF6, SF6, PCl5, NO, and BiCl3. The last one we're going to do are hydrates. Hydrates are substances that include water in their formula. The water is not actually part of the chemical substance, but it's reflected in the way that the formula is written. For example, CuSO4.5H2O says that for every 1 copper 2 sulfate, there are 5 water molecules bonded to it. No, the substance is not wet. It appears dry. There are some hydrates that will have a wet appearance, but they're almost perfectly dry to the eye and definitely to the touch. The dot is not a multiplication sign. This is chemistry, not math. So CuSO4.5H2O is written as copper 2 sulfate, so you do your naming rules for ionic compounds, and then you just use the prefixes that we use for molecular compounds to indicate the number of waters. Well, when something's got water in it, we say it's hydrated. So CuSO4.5H2O is copper 2 sulfate pentahydrate. Okay, if I'm going to do lead 2 acetate trihydrate, I have to remember my ionic naming rules for a transition metal. So I have lead 2 acetate, so lead 2 is Pb plus 2, acetate is C2H3O2 minus 1. So when I crisscross, I get Pb, C2H3O2 in parentheses 2, and trihydrate is .3H2O. Do the remaining 5. Now, assuming that you actually paused, here are the last 5. Manganese 2 chloride tetrahydrate is MnCl2.4H2O. Magnesium bromide hexahydrate is MgBr2.6H2O. Sodium carbonate decahydrate is Na2CO3.10H2O. Sulfuric acid monohydrate is H2SO4.1H2O. And iron 2 sulfate heptahydrate is FeSO4.7H2O. As I stated at the beginning, the only difference between these and the ionic compounds, and in this case sulfuric acid acids that we've done, is you need a dot and the number of H2Os, and you use the metric prefixes as the number for the hydrated part. So BaCl2.2H2O should be barium chloride dihydrate. LiCl.H2O is lithium chloride monohydrate. MgSO4.7H2O is magnesium sulfate heptahydrate. SrNO32.4H2O is strontium nitrate tetrahydrate. FeCl3.6H2O is iron 3 chloride hexahydrate. And MnO2.3H2O is manganese 4 oxide trihydrate. Once again, that's manganese 4 oxide trihydrate.